This will in turn lead to the possibility of coding in order to decrease the effect of errors caused by an information channel. We will see that our information measure may be used to analyze this type of coding as well as the type of coding already discussed. The central result of information theory and the most dramatic use of the concept of entropy will be discussed. This result in the form of Shannon's remarkable second theorem will use the entropy idea to describe how we may utilize an unreliable information channel to transmit reliable information. So, let us start with the definition of information channel. An information channel is described by giving an input alphabet we will call that input alphabet as A, consisting of input symbols denoted by A I, where I takes the value from 1 to R, which means the size of the input alphabet is R, and output alphabet which we denote by B, consisting of letters or symbols denoted by B j, where j is equal to 1 to S. So, what it implies that it is not necessary for me to have the size of input alphabet and output alphabet to be the same. With this alphabets, we have a set of conditional probabilities associated, given by probability of B j given A I for all I and j. Probability B j given A I is just the probability that the output symbol B j will be received if the input symbol A I is sent. The channel defined as given here is sometimes called zero memory information channel. A more general definition where the probability of a given output B j may depend upon several preceding input symbols or even output symbols is also possible. Such channels are referred to as channels with memory, and we can represent this channel graphically as shown in the figure here. So, we have the inputs to the channel given by A1, A2 up to AR, and this passes through a channel where we have been given the conditional sets of probabilities, and we have an output which is B1, B2 up to Bs. This is your output alphabet B, this is our input alphabet A, and this we can say is an information channel. So, a particular channel of great theoretical and practical importance is the binary symmetric channel. Binary symmetric channel denoted as BSC, and the channel diagram for the binary symmetric channel is shown in the figure here. So, in this case I have the input alphabet consisting of binary letters 0 and 1, and the output alphabet also consists of binary symbols 0 and 1. In this case the input size and output alphabet size are the same. So, this is the channel diagram for the binary symmetric channel, and as usual P bar is equal to 1 minus P. So, A1 is equal to 0 and A2 is equal to 1 and B1 is equal to 0 and B2 is equal to 1. Now, this channel is symmetric because the probability of receiving a 1 if a 0 is sent is equal to the probability of receiving a 0 if a 1 is sent, and this probability, actually this is the probability that an error will occur, is P. So, a convenient way of describing an information channel is to arrange the conditional probabilities of its output as shown in the figure. So, I have my inputs given by A1, A2 up to AR, and my outputs are B1, B2 up to BS. And so, these are my outputs and this correspond to my inputs, and these are my conditional probabilities. Probability of B2 given A1, and finally probability of Bs given A1, probability of B1 given A2, probability of B2 given A2, probability of Bs given A2, B1 given AR, probability of B2 given AR, and finally we have probability of Bs given AR. So, a channel can be described in a concise form as shown here. So, this will form a description of an information channel. Now, note that each row of this array corresponds to a fixed input, and that the terms in this row are just the probabilities of obtaining the various Bj at the output if the fixed input is sent. In order to simplify the description of an information channel, it will be useful to have an abbreviated notation for it. So, accordingly we will define probability Pij is by definition probability of Bj given Ai. So, this is equation number 1. So, if we use this notation, then we can write the description shown here in a concise matrix form as follows. We have P11, P12 up to P1s, P21, P22, P2s, and finally we have for the last row PR1, PR2 and PRs. So, this becomes a channel matrix. So, an information channel is completely described by giving its channel matrix. So, we will therefore use this matrix P interchangeably to represent both the channel matrix and the channel. Now, observe that each row of the channel matrix corresponds to an input of a channel, and each column corresponds to a channel output. Also note a fundamental property of this channel matrix: the terms in any row of the matrix must sum to 1. So, the summation out here will be 1, the summation out here similarly will be 1, and such matrices are also called Markov matrices or stochastic matrices. Now, this property follows since if we send an input symbol ai, we must get some output symbol. So, mathematically what it means is that probability of Pij, j is equal to 1 to s should be equal to 1 for I equal to 1 to up to r. Now, the channel matrix of the binary symmetric channel will be simply a 2 by 2 matrix with the entries given as P bar, P, P and P bar. So, this will be the channel matrix for the binary symmetric channel. Now, just as we did in the case of information sources, we may view the inputs and outputs of a channel in blocks of n symbols rather than individually. Thus, we define the nth extension of a channel. So, the definition will be as follows. Consider an information channel with input alphabet indicated by A, output alphabet indicated by B, and channel matrix P, then the nth extension of this channel has input alphabet which is indicated by A raised to n, with the letters of this alphabet indicated by alpha I, where I ranges from 1 to up to r raised to n, and the output alphabet of this extension of the channel is indicated by b raised to n, with the letters given by beta j, where j is equal to 1, 2 up to s raised to n, and for this channel the channel matrix is indicated by capital pi, with the entries in this matrix indicated by pi 1 1, pi 1 2 up to pi 1 s n, pi 2 1, pi 2 2 to pi 2 s n, and finally we have pi r n 1, pi r n 2, r raised to n, s raised to n. Now, each of the inputs alpha I consists of a sequence of n elementary input symbols. So, alpha I consists of AI 1, AI 2, up to a I n, and each of the outputs beta j consists of a sequence of n elementary output symbols indicated by y j 1, b j 1, b j 2 up to b j n, and the probabilities pi I j is equal to probability of beta j given alpha I. This probability consists of the product of the corresponding elementary symbol probabilities. So, just as was the case when we define the extension of information source, the extension of an information channel is not really a new concept, but just a new way of viewing an old concept. So, merely by looking at symbols of some channel in blocks of length n, we obtain the nth extension of that channel. Let us look at one example. Let us look at the second extension of the binary symmetric channel. So, second extension of the binary symmetric channel will have a channel with 4 input symbols and 4 output symbols, and its channel matrix will be as shown here. So, we will indicate the second extension of binary symmetric channel by this notation, and the matrix, channel matrix for this channel will be given as shown here. This is p squared, p squared, p p bar, p bar, p, p bar squared. So, this is a channel matrix of the second extension of a binary symmetric channel. Now, we note that the channel matrix of the binary symmetric second extension of binary symmetric channel may be written as a matrix of matrices. So, let P as before be the channel matrix of the binary symmetric channel, then the channel matrix of the second extension of the binary symmetric channel can be written as P bar P, P capital P matrix, P capital P, P bar capital P. Now, this matrix is known as the Kronecker square of the matrix capital P. In the more general case, the channel matrix of the nth extension of a channel is the nth Kronecker power of the original channel matrix. Now earlier in this course we used the information measure to measure the average amount of information produced by a source. The function of an information channel, however, is not to produce information, but to transmit information from the input to the output. We expect therefore to use the information measure to measure the ability of a channel to transport information. Now we proceed to investigate the amount of a channel information a channel can transmit. So let us look at the probability relationships in a channel. So let us consider an information channel with R input symbols and S output symbols, and this channel is defined by the channel matrix capital P. Now let us select the input symbols according to the probability P A1, P A2 up to P A R. We select the input symbols for transmission through this channel. Then the output symbols will appear according to some other set of probabilities, and let us indicate that set as P B1, P B2 up to P B J. Now the relationships between the probabilities of the various input symbols and the probability of the various output symbols can be easily derived. So let us do that. Now if you look at the output symbol Y1, for example, there are R ways in which we might receive output symbol B1. So if A1 is sent, B1 will occur with probability P11. If A2 is sent, B1 will occur with probability P21, etc. Therefore, we can write probability of A1 P11 plus probability of A2 P21 plus probability of A R, probability of R1, this will be equal to probability of B1. Similarly, we can write probability A1 P12 plus probability A2 P22 AR probability R2 is equal to probability of B2, and finally probability of A1 probability P1s plus probability A2 probability 2s AR probability Rs is equal to probability Bs. This sets of relationship, let us call as equation number 5. So, these equations provide us with the expression for the probabilities of the various output symbols if we are given the input probabilities P A I and the channel matrix capital P, that is the matrix of conditional probabilities, probabilities of B j given A I. Now, for a further discussion, we will assume that we are given the probabilities P A 1, P A 2 up to P A r and the conditional probabilities probability B j given A I, so that probability of B j's may be calculated from this equation. Note however, that if we are given the output probabilities, that is probability B 1 up to B s and probabilities of B j given A I, it may not be possible to invert the system of linear equations in order to obtain the probabilities P A I. For example, if we take a binary symmetric channel with P equal to half, then any set of input probabilities will lead to output symbols which are equiprobable. So, in general there may be many input distribution which lead to the same output distribution. If we are given the input distribution, on the other hand, we may always calculate a unique output distribution with the aid of these equations. In addition to the marginal probabilities of the output symbol, there are two more sets of probabilities associated with an information channel, which we may calculate from the input marginal probabilities and the channel matrix. So, let us look at those probabilities. So, we have been given probability of P A I and we have the channel matrix. So, we have been given conditional probabilities B j given A I. Now, according to Bayes' law, the conditional probability of an input A I given that an output B j has been received is probability A I given B j is equal to probability of B j given A I multiplied by probability A I divided by probability B j, and this can be written as this expression has been substituted by this based on a earlier observation given by this sets of equation. So, the probabilities A I given B j are sometime referred as backward probabilities in order to distinguish them from the forward probabilities, which are indicated by probability B j given A I. Now, the numerator of the right side of this equation is the probability of the joint event A I B j. So, this is equal to probability B j given A I probability A I, and this quantity is also equal to probability of A I given B j multiplied by probability B j. Now, let us illustrate the calculation of the various probability associated with an information channel. We again take an example of a binary channel, that is, we have input alphabet A consisting of two letters 0, 1 and output alphabet consisting of two symbols again 0 and 1, and we assume that the channel matrix that is the conditional set of probabilities B j given A I has been given to us as follows. So, sum of this row is 1, again the sum of this row is equal to 1 as discussed earlier. Now, we associate the rows and columns of this matrix with the input and output symbols in the natural order. Therefore, probability of B equal to 0 given A equal to 0 is 2/3, probability of B equal to 1 given A is equal to 0 is 1/3, and similarly for these entries. So, we also assume that probability of A equal to 0, A 1 equal to 0 is equal to three-fourth, and probability A equal to 1 is equal to 1/4. Now, this information can be neatly summarized as shown in the figure here. So, the probability of the output symbols 0 and 1 can be obtained with the help of these equations, and probability of B equal to 0 is equal to probability of 0 given 0 was transmitted multiplied by probability of 0 transmission, or probability of receiving 0 given 1 was transmitted multiplied by probability of 1 being transmitted. So, using this we can write this as 3/4 multiplied by 2/3 plus 1/4 multiplied by 1/10, and this comes out to be 21 by 40. So, similarly probability B equal to 1 is equal to 3/4 by 1/3 plus 1/4 multiplied by 9 by 10, and this is equal to 19 by 40. So, as a check, probability of B equal to 0 plus probability of B equal to 1, this should sum up to equal to 1. Now, the conditional input probabilities can be obtained as probability of A equal to 0 given B equal to 0 is equal to 3/4 multiplied by 2/3 divided by 2140 is equal to 20 by 1. One-fourth multiplied by 9 by 10 whole over 19 by 40 is equal to 9 by 90. The other two backward probabilities may be similarly obtained. So, probability of A equal to 1 given B equal to 0 is equal to 1 by 21, and probability of A equal to 0 given B equal to 1 is equal to 10 by 19. It is to be noted that this plus this is equal to 1, again this plus this is equal to 1, and if you are interested in calculating the probability of various joint events, then we can calculate the probability of A equal to 0, B equal to 0 as probability of A equal to 0 given B equal to 0 multiplied by probability of B equal to 0, and this is equal to 20 by 21 multiplied by 21 by 40. So, this is equal to half. Now, the various outputs symbols of a channel occur according to the set of probabilities which is given by probability Bj. Note that the probability of a given output symbol Bj is Pbj if we do not know which input symbol is sent. On the other hand, if we do know that input symbol is Ai, then the probability that a corresponding output will be Bj changes from probability Bj to probability Bj given Ai. So, once the transmission of symbol Ai is known, the output symbol probability Pbj changes to probability of Bj given Ai. Likewise, we recall that the input symbol Ai is chosen with probability Pai. If we observe the output symbol Bj, however, we know the probability that Ai is the corresponding input symbol is Ai given Bj. So, now let us focus our attention on this change induced on the probabilities of the various input symbols by the reception of a given output symbol Bj. We shall refer to probability Pai as the a priori probabilities of the input symbols, that is the probabilities of the Ai before the reception of an output symbol, and probability Ai given Bj will denote it as a posteriori probabilities of the input symbol, that is the probability after the reception of Bj. We know that we can calculate the entropy of the set of input symbols with respect to both these sets of probabilities. So, let us calculate the a priori entropy of A, and so a priori entropy of the source A will be given as H A equal to probability Pai log 1 Pi summation over all Ai's, and that will denote it by capital A, and a posteriori entropy of A when Bj is received is given as Ai Bj log of over all Ai's. Now, the interpretation of this two quantities follows directly from Shannon's first theorem. Ha is the average number of binates needed to represent a symbol from a source with the a priori probabilities given by Pai, I is equal to 1 to R. This is the average number of binates needed to represent a symbol from a source with the a posteriori probabilities Pai given Bj for all I is equal to 1 to R. So, let us calculate this two quantities for a binary symmetric channel which we considered earlier in the class today. So, we will take that example again. So, the binary symmetric channel is given by this channel diagram. Probabilities of 0 transmission, let us assume equal to 3/4 and probability of transmitting 1 is equal to 1/4. Now for this we can calculate the entropy of the source, that is equal to 3/4 log 4/3 plus 1/4 log 4. This is equal to 0.811 bits per symbol. If we receive the symbol 0 at the output of the channel, then our a posteriori probabilities, which we have calculated earlier, and using those a posteriori probabilities we can calculate it a posteriori entropy as follows. So, a posteriori entropy of A when 0 is received is given by this expression. This is equal to 0.276 bit per symbol. Now, if we receive the symbol 1, on the other hand, a posteriori entropy of A will be given by is equal to 0.998 bit per symbol. Hence, if a 0 is received, the entropy, that is uncertainty about which input was sent, decreases, whereas if a 1 is received, our uncertainty increases. In today's class, we have looked at a definition of information channel and seen how to represent an information channel, and also looked into the calculation of the various probabilities associated with an information channel. In the next class, we will revisit Shannon's first theorem and generalize this Shannon's first theorem from the viewpoint of an information channel.